and welcome to Lecture 9 on continuity and limits. All right, so first of all, let's talk about what a limit is. The limit of a function f of x at a is how the function behaves as x gets really close to a. So I've drawn two examples of limits here. We can take the limit of the function x squared minus 9 as x approaches 3. So what happens to the function x squared minus 9 as we get really close to x equals 3? Well, we get closer and closer and closer and closer and closer, and we eventually reach this point right here. So one way to evaluate a limit is simply to plug in the value of x at a. So, for example, if we want to take the limit, this limit here of x squared minus 9 as x goes to a, one option is to just plug in x equals 3, and we get f of a is equal to 3 squared minus 9, which is simply 0. And looking at the plot, sure enough, as we get closer and closer and closer to a value of x equals 3, then the function approaches value of 0. Okay, another example of a limit is still as x goes to the quantity 3, but now we're taking the limit of the function x squared minus 9 divided by x minus 3. What happens if we just plug in the value of x equals 3? Well, then we would have 3 squared minus 9 divided by 3 minus 3, which is equal to 9 minus 9 divided by 3 minus 3, which is equal to 0 divided by 0, and the universe blows up because you can't divide by 0. All right, so what actually happens as we get closer and closer and closer to a value of 3? Well, one way to answer this question is to try to factor the function x squared minus 9 divided by x minus 3 and cancel terms. So one way to factor the numerator is as x minus 3 times x plus 3, and then we want to divide by the denominator x minus 3. If we do this division, we can now cancel this term and this term, and we want to take the limit as x goes to 3. So now we plug in the value of 3, and we simply get x plus 3, which is 3 plus 3, which is equal to 6. All right, as you look at the plot, as you get closer and closer and closer to a value of x equals 3, we approach the value of y equals 6. So this checks out. All right, so limits can get kind of crazy. Remember that the logarithm can only be evaluated for values of x that are greater than 0. So there's actually a typo in this slide. There should be a 0 here. So as we get closer and closer and closer to 0, what happens to the natural log of x? We can't ever get to 0 because we only can plug in positive values, but what happens as we get closer and closer to it? So let's look at the plot. As we move over here to the left, the value of the natural log of x drops and drops and drops and approaches minus infinity. So as we go here, it approaches minus infinity. Now, note that you can't actually set something equal to minus infinity. That doesn't actually work. Nothing ever exactly equals minus infinity. So we are going to say that this approaches minus infinity. And in other words, the limit does not exist. So formally, if the limit either approaches minus infinity or approaches positive infinity, that means that the limit does not exist. All right, so what about evaluating the limits of other functions? Well, sometimes the value of the limit depends on how we approach the quantity. So for some functions, if we approach the value of a from the left, or if we approach the value of a from the right, we're going to get a different answer. So we denote these as the right hand and left hand limits, and we put a little positive sign or a little negative sign in a superscript of a to denote whether we are approaching it from the right, which is the positive one, or if we're approaching it from the left, which is the negative one. One example of a function that has a different left and right hand limit is 1 over 1 minus x as x approaches 1. All right, so if we're approaching x equals 1 from the left, that means that x is less than 1. if that happens, then this denominator is, for example, 1 minus 0.99999, and that is a positive number. So we have a positive denominator down here, and hence the function evaluates as something that is positive, but the denominator gets smaller and smaller and smaller, so the limit does not exist and it diverges off to positive infinity. So as we take the limit as x goes to 1 from the right of the function 1 over 1 minus x, this is a divergent limit that does not exist and it approaches positive infinity. Now, if we approach from the other side, this means that we are evaluating the denominator, which is 1 minus 1.00001, for example, or smaller and smaller and smaller numbers. This is equal to minus 0.0001, and it is a negative number. So the function evaluates as something negative, but once again, this denominator is getting closer and closer to 0, so the function flies off to minus infinity. So if we take the limit as x goes to 1 from the right-hand side, then, oh, sorry, I think I got this backwards. If we approach from the left-hand side, we have a minus sign there. If we approach it from the right, we have a positive. And this evaluates out to being minus infinity, and the limit does not exist, but it is a different limit than if we approach it from the left. All right. So a second example of a left and right hand limit is the function, the absolute value of x divided by x. Since you have the absolute value of x divided by itself, the value always comes out as either being positive 1 or minus 1, but whether or not it's positive or minus negative depends on if x is less than 0 or greater than 0. So if x is less than 0, then absolute value of x divided by x is going to be minus 1, and we're going to get this limit. And then as x approaches 0, when the absolute value x divided by x is, and x is positive, we're going to approach it as the value of 1. All right, so there's a lot of different things that we've covered already. We've talked about how to evaluate limits in different ways. So you can either simply plug in the value of a, you can try to cancel first and then plug in the value of a. Sometimes limits don't exist and they fly off to infinity. And sometimes it matters whether or not you approach the limit from the left or if you approach the limit from the right. All right, now let's introduce a series of limit rules that you can apply to any function to help you find the limit. The first one of these limit rules is that the limit of the sum is the sum of the limits. So if we have the limit of two functions that are added together, we can take the limit of each of those functions separately. Similarly, if we have the limit of a difference, it's the difference of the limits. So you can split up limits on plus signs and minus signs. So let's apply this rule to this function here, and we would get that we have the limit as x goes to 5 of 2x squared. Now we can split it up on this minus sign and this plus sign. So let's split it up on the minus. The limit as x goes to 5 of 3x plus the limit as x goes to 5 of 4. All right. Now, the next rule is that if we have a constant inside of a limit, so some of the constants that we have here are 2 and 3, that those constants can be factored outside of the limit. So let's factor those out. So we have rule 2, and we end up with 2, the limit as x goes to 5 of x squared, minus, now we can factor out that 3, limit as x goes to 5 of x plus, now the 4 factors out and leaves nothing else in there, so we simply have 4. So if you have the limit of a constant, that is just the constant itself. All right, so next we have that the product of limits is equal to a limit of a product is equal to the product of the limits, and similarly the limit of a power is equal to the limit raised to that power. So these are the same thing, it's just that this one is extended so that you have n things multiplied by itself. Okay, so we have a few places that, or one place that a product shows up here. We have this x squared here. So this becomes 2, the limit as x goes to 5 of x squared, minus 3, the limit as x goes to 5 of x plus 4. So this is rule 3. So we don't have to use this fourth rule here, but if you have the limit of a quotient, it is the quotient of the limit. If you have the limit of a quotient, it is the quotient of the limits, given that the denominator does not equal to 0. And we'll see in a minute how that applies. All right, so now let's actually finish taking this limit. Now that we have everything boiled down to as simple as possible, remember that one thing we can do is just plug in the value of a. The value of a here is 5. So we end up with 2 times 5 squared minus 3 times 5 plus 4, which is equal to 50 minus 15 plus 4, which is equal to 39. So now you have taken the limit of this polynomial as x approaches 5. All right, now, second example, let's take the limit of a ratio of polynomials. So in the numerator, we have a cubic, and in the denominator, we have a linear function. All right, so remember that this fourth rule, if we have the limit of a quotient, it's the quotient of the limits, given that the denominator does not equal 0. So let's do a little side work over here. We want to know, does the limit as x goes to 5 of 5 minus 3x, what is that quantity? Is that quantity equals to 0? Well, let's plug in x equals 5, and we get 5 minus 15, which is equal to minus 10. This does not equal 0, so we can apply rule 4 and obtain our limit. So we have the limit as x goes to 5 of x cubed plus 2x squared minus 1 divided by the limit as x goes to 5 of 5 minus 3x. All right, so you can do this in two ways. You can either apply the limit rules that we used up above, where we split up this numerator and denominator on the sums and the subtractions, and then apply the products, etc., etc., or we can simply just plug in the value of x equals 5. In this particular case, they come out to be the same thing, and if we just plug in the value of 5, we get 174 divided by 10, which is equal to 17.4. So this is a good self-study section if you need to pause the video and work through how to take this limit using the limit rules. Please take the time to do that. All right, so that is how you take limits. Now, why would you actually want to take a limit? Well, one reason to take a limit is to ask whether or not a function is continuous. So a function is continuous, we can say this in a very hand-wavy way, if we don't have to pick up our pen to draw it. So consider the function y is equal to x squared minus 9 divided by x plus x minus 3. We took the limit of this earlier at x equals 3, and we got the value of 6. So the value of x squared minus 9 divided by x minus 3 doesn't exist at x equals 3, but let's say that as soon as we get to exactly x equals 3, we plug in 6. And in this case, we don't have to pick up our pen in order to draw that line. Let's suppose instead that we use the same function for everything except x equals 3, except when we get to exactly x equals 3, we jump up to 7. In this case, we have to pick up our pen in order to draw this line, right? Draw this function. So this curve over here is continuous, whereas this over here is a discontinuous curve. Formally speaking, a function is continuous if the limit as x goes to a from the left-hand side and x goes to a from the right-hand side are the same thing. So if for every value on the x-axis, the limit as we approach from this side and this side are the same, then it is a continuous function. Otherwise, if we approach the limit from this side and this side, that they are the same, but they do not equal the function itself. So you have to have that the left-hand limit and the right-hand limit equals the function. All right, so is a self-work. Think about the function x minus 3 times x plus 5 divided by x minus 3. What value of a would you have to use at exactly x equals 3 to get this curve to be a continuous curve? All right. Pause the video here, work this out. What do we get? Well, what happens is we take the limit of this first part of this function. Well, one way to take the limit is to cancel. So let's cancel the x minus 3 and the x minus 3. Now, if we plug in x equals 3, we have 3 plus 5 equals 8. So the value of the limit of f of x as we approach the value of 3 is equal to 8. So if we make a equals to 8, then for every point, we'll have that the left limit, the right limit is equal to the function, even at x equals 3. All right, so a value of a equals 8 will make this a continuous function. All right, with that, I'm going to leave you with the self-study question, and we'll chat in class.